Welcome back to the deep dive. We've got a really interesting, pretty technical stack of material today. We're going deep into digital signal processing,
hmm
specifically looking at something fundamental, really. Signal timing and, well, the distortion that can happen with filters.
Yeah, it's all about avoiding what engineers sometimes call signal smearing.
Hmm.
And our goal here really is to get clear on two key ways we measure time delay, phase delay, and group delay.
Okay.
And then sort of show how this thing called the linear phase filter, which is built on this really neat mathematical symmetry, kind of gives us the gold standard for keeping signals clean, whether that's data or, high fidelity sound.
Right, let's jump straight in then, because the stakes are pretty high, aren't they? You pass a complex signal like music or maybe a data stream through some system.
System, yeah.
And the different frequencies within that signal, they might not all travel at the same speed. They can arrive at different times.
Exactly, and that's the smearing. The signal shape gets distorted because its parts are, well, out of sync.
So this whole deep dive really boils down to understanding the difference between delaying the wave itself, the carrier wave, and delaying the actual information that wave is carrying.
That's the core distinction. Spot on.
Okay, so let's tackle this delay duo, as the sources call them. First up, phase delay. What exactly is that?
So phase delay, often written as tau phi, it's basically the time shift that each individual sine wave component experiences.
Each frequency on its own.
Exactly. Think of it like the delay of the carrier wave at one specific frequency.
Yeah.
If you're analyzing a narrowband signal, just a small slice of frequencies, phase delay tells you about the timing of that individual ripple, so to speak.
Got it. So the individual ripple. Now, the other one is group delay. And I'm guessing this is the one that often matters more in practice.
Yeah, absolutely. For a lot of applications, group delay, or TEG, is the crucial one. It measures the time delay of the envelope of the signal.
The envelope, meaning the overall shape,
Yeah,
the information.
precisely. The information package. If you have a signal like an AM radio wave, or maybe the sharp attack, the beginning of a sound like a kick drum that's the envelope, group delay tells you how long that takes to get through the system.
Okay, so going back to the kick drum example, the group delay tells us when the thump arrives, the main impact, while the phase delay might tell us more about the timing of some, I don't know, high-frequency resonance within that thump.
That's a good way to think about it, yeah. For any signal that carries information across a band of frequencies, broadband signals, modulated signals, group delay is key. Mathematically, it's interesting, too.
How so?
Well, phase delay comes from the total phase shift divided by the frequency. But group delay, it's derived from how fast the phase is changing with frequency. It's the slope of the phase response curve.
Ah, the rate of change.
Exactly. And that slope is intrinsically linked to how the information in the envelope propagates.
Now, the sources really highlight the consequence if these two delays aren't the same. If Haas isn't equal to tug, that's bad news, right? Distortion.
It is. Big time. If they differ, the information in the envelope arrives with a different delay compared to the carrier waves making it up. The waveform literally changes shape. It gets smeared out.
And this isn't just theoretical. You can actually hear this.
Oh, definitely, especially in audio. The sources mention studies showing that in that really critical mid-range, maybe 1 to 4 kilohertz, listeners can perceive group delay differences down to about 1.6 milliseconds.
Wow, 1.6 milliseconds. That's tiny.
It is incredibly small.
Yeah.
But our ears are sensitive to that timing information. It shows just how crucial consistent timing is for, high-fidelity sound reproduction. Any noticeable difference there, and the clarity, the sharpness, it just degrades.
Okay, so inconsistent delay messes things up. We need a filter, ideally, that treats every single frequency component exactly the same way in terms of time. Same delay for the carrier, same delay for the envelope.
That's the goal.
Which brings us to the solution presented in the sources, the linear phase filter.
Exactly. A filter is called linear phase if it's phase response. Well, it changes linearly with frequency. If you plot phase versus frequency, you just get a straight line going downwards.
Phase is directly proportional to frequency.
Right. And the magic is if you have that perfectly linear phase response, say PAPO where C is just some constant,
Okay.
then when you calculate the phase delay, which is on the group delay, which is the negative derivative part O, they both come out to be exactly equal to that constant C.
So phi equals seg, and they're both constant. Same value for all frequencies.
Precisely. Every frequency component gets delayed by the exact same amount of time.
See? Which means no phase distortion. The filter doesn't smear the signal at all. The output is just a perfectly time-shifted copy of the input.
That's the beauty of it. The only effect is that constant delay. And this is why engineers designing systems where a signal shape is critical almost always turn to a specific type of digital filter, the FIR filter, finite impulse response.
Why FIR specifically?
Well, FIR filters have some really nice properties. They're inherently stable, for one. And structurally, they're feed-forward or all-zero filters. They don't have feedback loops like II filters do.
Yeah.
This structure makes it, well, relatively straightforward to design them to have exactly linear phase.
And how do you actually achieve that? What's the trick in the design?
It's actually surprisingly elegant. It comes down to the filter coefficients, the numbers that define the filter's operation. You just need to make sure those coefficients are either symmetric or antisymmetric around the center point of the filter.
Just symmetry. That's it?
That symmetry in the coefficients mathematically forces the phase response to be linear. It's a direct consequence. And it tells you the delay for an FIR filter of lengths n.
N coefficients or N taps.
Right, n taps. The constant group delay it introduces is exactly n12 samples. Perfectly predictable.
Okay, so symmetry gives perfect timing. But there's always a catch, isn't there? The sources mention 4 distinct types of linear phase FIR filters based on whether the length n is odd or even, and whether the symmetry is, well, symmetric or antisymmetric. This seems to impose some limitations.
It absolutely does. You don't get that perfect timing for free. These symmetry requirements create constraints on what the filter's frequency response can actually do.
Can you give an example?
Sure. Let's take a type 2 filter. That's one with an even number of taps and in symmetric coefficients. Because of that structure,
Yeah.
its frequency response is mathematically forced to be exactly 0 at the highest frequency, which we call pi in normalized frequency terms. Always 0 there.
Which means, what can't you do with it?
It means you simply cannot design a good high-pass filter using a type 2 structure. A high-pass filter needs to pass high frequencies, not block them entirely at the very top end.
I see. The structure itself prevents it.
Exactly. And similarly for the other types, the antisymmetric ones, types 3 and 4, they have forced zeros at other important frequencies. Like type 3 must be 0 at both frequency 0 DC and the highest frequency pi. So it can't be low pass or R high pass. It's only good for bandpass designs.
And type 4.
Type 4 has an even length and antisymmetry. It's forced to be 0 at frequency 0 DC. So no low pass filters with type 4 either.
That's fascinating. So the very thing that guarantees perfect timing, the symmetry, restricts what kind of frequency selection you can achieve with each filter type. It's trade-off right from the start.
Precisely. You choose the type based on the delay characteristics and whether its inherent frequency constraints fit the job you need it to do.
Okay, let's shift gears slightly. We've talked about the ideal linear phase filter. Now, the practical reality of actually making one. This is where engineering meets mathematics, right? The ideal versus the real.
Right, because the ideal frequency response, like a perfect brick wall filter that passes everything below a certain frequency and stops everything above it instantly, well, that filter, mathematically, requires an impulse response that goes on forever. It's infinite in duration.
And we obviously can't build an infinitely long filter in practice.
Nope, can't do it. So the first step in any practical design is you have to truncate that ideal infinite response. You have to cut it off, make it finite, and you also have to shift it in time to make it causal, meaning the output can't happen before the input arrives.
So you take the ideal infinite response and basically chop it off using like a rectangular window.
You could. That's the simplest way. But chopping it off abruptly like that, with a sharp rectangular window, that creates a sudden discontinuity in the time domain.
And discontinuities are generally bad in signal processing.
Very much so. That sharp edge in time translates to ripples and overshoot in the frequency domain. It's called the Gibbs phenomenon. You get these oscillations in the pass band and stop band near the cutoff frequency. It messes up your filter's performance.
So how do designers get around that?
They use smoother window functions instead of the abrupt rectangle. Things like the Hamming window, Hamming Blackman. These windows taper off gradually towards 0 at the edges. No sharp cliffs.
Okay. Smooth window, less ripple. Sounds good. But there's a trade-off again, isn't there?
Always. This is the classic FIR design trade-off. The smoother window definitely reduces those Gibbs ripples, which is great. Gives you much better attenuation in the stop band, less distortion in the pass band.
Right.
But it smears out the transition between the pass band and the stop band. It makes the cutoff less sharp. You increase the transition width.
Ah, so if my design specs demand a really sharp, narrow transition band.
Then using a smooth window forces you to compensate by making the filter much longer. You need to increase n, the number of taps.
Which means more calculations, more memory, potentially more delay.
Exactly. More computational complexity. It's a direct trade. Smoother window means less ripple but wider transition, unless you pay the price with a longer, more complex filter.
Which leads us neatly into optimization, right? The sources mention that just using standard windows isn't always the most efficient way. There are better algorithms.
Oh, absolutely. Windowing is conceptually simple, but it's not optimal. Methods like designing for least squares error, or especially the Parks-McClellan algorithm, which uses the Remez exchange algorithm, these are much more powerful.
How do they work differently?
Instead of just trying to make the impulse response smoother, they directly try to minimize the maximum error across the frequency bands, passband and stopband. They aim for an equiripple response. The ripples have equal height across the band.
And the benefit is efficiency.
Huge efficiency gains. The source material gives a great example. For a specific set of filter requirements, using a standard window method might demand a filter length of, say, N80 taps.
Okay, 80 taps.
But using an optimized approach, like least squares designed for the same requirements, they got it down to N33 taps.
Wow, 80 down to 33. That's less than half.
Exactly. Same performance specifications, same perfect linear phase, but massively less computation required. That's a huge win in any real-time system. It really shows why these optimization techniques are standard practice in serious DSP design.
Okay, so let's try and wrap this up. What's the big takeaway for you, the listener, from this deep dive?
Well, I think it's achieving linear phase is really fundamental if you care about preserving the shape of your signal. It's the engineering solution to stop that smearing effect we talked about.
Because it forces the delay of the information, the group delay, to be exactly the same as the delay of the individual frequency components, the phase delay, and makes both constant.
Right. They travel together, perfectly synchronized. So whether you're working on, I don't know, high-end audio or medical imaging or maybe a critical communication link, understanding why you want TOC and knowing that FIR filters are the go-to tool to achieve it, that's really valuable knowledge.
It drives your design choices, including those trade-offs between filter sharpness, ripple, and computational cost. Now, we established throughout this that delay is, causal. Things happen after the input. But here's a final thought from the sources to really chew on. Apparently, even causal filters can sometimes exhibit negative group delay.
Yeah, this one is genuinely weird when you first encounter it. Negative group delay.
Meaning the peak of the signal's envelope, the information, can actually appear at the output before the corresponding peak has even fully arrived at the input, it sounds like. Well, like time travel.
It really does sound like it.
Yeah.
But, crucially, causality isn't actually violated. The entire signal hasn't passed through the filter yet when this happens.
So what's going on? How can the output peak arrive early?
It's kind of like the filter is making an educated guess. If the incoming signal has a predictable shape, the filter can effectively see the leading edge of the envelope coming. And based on that predictable shape, it can sort of reconstruct or anticipate where the peak will be and start outputting that peak slightly ahead of time relative to the input peak's arrival.
So it's an illusion of prediction based on the signal's own structure.
Exactly. It's a fascinating effect. It relies entirely on the signal having enough structure and predictability for the filter to anticipate its peak. It really makes you think, doesn't it? What does that imply about the nature of information itself and the predictability that's often inherent in the signals we process?
A very provocative thought indeed.
Yeah.
Something for you all to mull over.